Good morning, everybody, and thank you for the introduction, Leonid. So, my talk will be about the frequency domain methods, today specifically in discontinuous and sliding mode control systems, and which provides maybe a slightly different view on in the area of sliding mode control compared to what we're used to hear, used to see. So it's just a view from a different perspective what concerns the sliding mode control system. And specifically, so here in this table there is some problems that can be solved and are solved by the frequency domain methods. So here we have the methods. Some of them are describing function based, I would call them the describing function and harmonic balance, the describing function and phase deficit, the bias function and equivalent gain, locus of a perturbed delay system, bias function and equivalent gain through the LPRS. So it's, where what is based on the describing function is an approximate approach. What is based on the LPRS method is an exact approach, but in some cases they solve the same problems. And the problems are analysis of chattering or periodic motions, analysis of convergence, orbital stability, stability of the equilibrium, transient oscillations, and effect of external signals or control or disturbance inputs. So that's the transient processes in these systems, discontinuous and sliding mode control systems. Whatever is given in red are the original methods that are developed by me, and I will give more focus to that in this presentation. However, of course, they have a background of the describing function, so that's why. Sorry about those who will find it like the basic material, so the textbook material. I will, because it's wonderful but forgotten methods, so I will briefly go through this, and it would be beneficial for explanation of this subsequent material. So what is and we will start with this describing function method. So what is that? What is the describing function? It's a function which shows the propagation of the first harmonic through a nonlinearity. In that sense, it's a certain complex game by which we can replace the nonlinearity in analysis of, for example, self-excited oscillations, but not only that. And it is based on the Fourier series, and if the output of the nonlinearity, if the input to the nonlinearity is assumed to be harmonic and the output non-harmonic by periodic, we can present the output as a Fourier series, or sum of Fourier series. And if after that, that's for this we represent it as a Fourier series, if after that we have the linear part, which is or linear dynamics, which are a low-pass filter such that all high harmonics are, let's say, rejected by this low-pass filter, so that these coefficients of the Fourier series we can assume to be zero. Then it's here. Then in the let's say in the closure of the system, we say that Z is also a harmonic signal which comes as X with a negative sign, and all this recycling or cycling of this process happens. And in this case, because the high harmonics are rejected in Z, we can also ignore them in Y, although they exist, but we can just disregard them in our consideration and consider propagation of only the first harmonic through this loop. And in doing that, we can easily obtain the results which are summarized in the harmonic balance. However, the harmonic balance was developed even before the describing function using different, let's say, from a different perspective. But when we know what the describing function is, we can formulate this harmonic balance in a much simpler way and derive the harmonic balance in, let's say, very, very easily, rather than from the original formulation by Krylov and Bogolyubov. So if we know what the harmonic, what the describing function. So what can we do? What problems can we solve if we know the harmonic balance, which will be formulated in the next slide? So we can find the frequency and amplitude of the oscillations, self-excited oscillations in the system that may occur, and also determine if these oscillations can exist in the system and under what conditions they can exist in the system. With regards to the sliding mode systems, because we know that the chattering is oscillations, self-excited oscillations, we can immediately find the conditions when this chattering exists. So we basically that will be our approach at a certain point. So once we replace the nonlinearity now with the describing function, we can write that the approximately the output of this nonlinearity is the describing function by x. And again, the describing function is a complex quantity which has a real part and imaginary part. However, if the nonlinearity is a single-valued symmetric, odd symmetric nonlinearity, then we can easily prove that the q prime, which is the imaginary part, is zero, and we have only the real quantity in this case. And easily from this property of the closing loop, so we will find if we replace our nonlinearity with this notation and go to the loop, let's say, equations, we can easily find that the harmonic, we will arrive to the formulation of the harmonic balance principle, that the product of the describing function as a function of the amplitude, it's a replacement of the nonlinearity, but this is it is a function of the amplitude of the oscillations of the harmonic signal, which is the input to this nonlinearity. So it's, we replace it with the linear gain, but the nonlinear dependence on the amplitude is retained in this. And by the transfer function of the Planck, the frequency of these oscillations should be equal to -1. Or very conveniently, we can rewrite them. We can separate the transfer function of the frequency response, which is a function of the omega, and n describing function, which is a frequency of a, into different sides of the equation, which would provide us with sometimes more convenient way of solving these equations. And separately, if we consider, because it's a complex equation, we can separately consider equations of the magnitudes, and we will get the magnitude or amplitude balance, and separately equation of phases, and then we can have a phase balance. If we have an ideal relay, that's what we have in many cases in sliding mode control, as our nonlinearity in the system. In this case, our so these will be the equations of the linear part, with sigma being the sliding variable, and sliding variable is the input to this signal nonlinearity, which gives us the control u. So for this nonlinearity that we have in the system, we can find that the describing function is simply for c over pi a, where c is the magnitude of this relay, and a is the amplitude of the harmonic signal, which is the input to this relay nonlinearity. And now, if we draw the solution of the harmonic balance equation of this form, so that we have here we have the frequency response of the linear plant, frequency response of the linear plant, or the Nyquist plot, if we draw it in a complex plane. And here we have the negative reciprocal of the describing function as a function of omega. If we draw them on the complex plane, so we will have the following picture. So because the relay has this describing function, which is a real quantity, doesn't have an imaginary part, so in a complex plane, the negative reciprocal of this will be simply minus pi a over 4c. So it's also a real quantity, negative quantity, which is given here by this blue line, so where each point corresponds to a different value of a. And here we have different Nyquist plots. For example, this dashed line is for the first order system, and the solid line and dotted lines are for the third order system. And we can easily see that for the first order system, we don't have a point of intersection between the negative reciprocal of the describing function and the Nyquist plot, except for the zero. But this is a tricky thing. If we have really an intersection there, I would say no, we don't have an intersection there, because the phase balance is not met. The condition of the phase balance is not met, because here we have phase balance for the relay nonlinearity, phase characteristic of the relay is 0, and for the first order we have maximum 90 degrees, and we need to obtain minus 180. So that point is not the point of intersection. They both just approach 0, become an infinitely small values, but there is no intersection between these lines. But we have definitely an intersection point between the solid line and this blue line, or dotted line and blue line, and respectively we have this would be a point corresponding to self-excited oscillation, or this would be a point corresponding to self-excited oscillation. So we have, let's say, we can solve the problem of finding the frequency and amplitude of self-excited oscillations. In specifically sliding mode control systems, if we add certain dynamics to the principal dynamics, we sometimes refer to that as parasitic dynamics. So this will, the dynamics of actuators and sensors, we will necessarily get chattering in the system, because these dynamics of the sensors and actuators will increase the relative degree of the system, so that we cannot have first order. We will have third, fourth, fifth, and so on orders. So that's why we cannot avoid having a point of intersection with this line. So, and that's why we will necessarily have chattering in the real sliding mode control system when we add actuators and sensors to the control system. So because we have these additional dynamics in the loop in series with the plant, which is actuator dynamics, sensor dynamics, or even the digital controller processing time, which introduces the delay, we will have this effect of intersecting by the Nyquist plot of the negative reciprocal of the describing function. And this happens due to the increase of the relative degree of the linear part of the system, of this linear dynamics. So in the actual system, in the ideal sliding mode, we consider it to be 1, for example, if we have, let's say, first order classical sliding mode, the relative degree is 1. Once we add actuators, sensors, and processing time, it becomes higher. And actually, it's in reality, it's high order, or high value, approaching infinity, because we can go to the consideration of smaller and smaller details. For example, we can go to the actuators and say, okay, this is a second order system. In actuators, we have a motor. Okay, motor is another second or third order system. in the motor is controlled by an amplifier. Okay, amplifier is also adds dynamics. In amplifiers we have transistors. Okay, each transistor also adds more dynamics and more and more and more. So we cannot fix the relative degree and say, okay, this our system is of second relative degree or third relative degree. We need to understand that we have more and more dynamics. Maybe they're small, but even this small, let's say, small dynamics increases the relative degree of the system and results in chattering. So it may be very high frequency chattering, but it's still chattering and we cannot avoid it. So the results of analysis through these models would differ from no chattering. So if we use different models, we can obtain, let's say, no chattering if we don't use the models of the actuators. So let's say no chattering, to getting chattering similar to the observed in the actual system. And I think from the at least practical point of view, it would be much more valuable to have detailed dynamics so that we obtain the results matching to what we have in real life. In real life, we will have chattering. We will have oscillations in this system. So, chattering is high-frequency oscillations in slightly more controlled system. They occur, which occur because of the presence of non-Lipschitz nonlinearities. So if we had Lipschitz nonlinearities, there would be a possibility to avoid chattering even, let's say, with high order dynamics. Like what we have in, let's say, linear systems with linear controllers. We are trying to reduce the gain, control gain to such value that we come to the, let's say, stability domain of the system, stability for the equilibrium point that we have. So that would be possible, but with the non-Lipschitz nonlinearities, like this relay, the whole nonlinearity describing function or reciprocal, negative reciprocal of the describing function, they start at zero, at the origin. So that's why we cannot avoid the point of intersection. If we had a non-Lipschitz nonlinearity, the initial point might be somewhere here, corresponding to zero amplitude, and then it would increase to those. For non-Lipschitz nonlinearities, it starts from this point. So we can not avoid having a point of intersection here, and we cannot avoid having chattering. Yes. Chattering also. Chattering implies instability of the equilibrium point. So it's essentially, if we say that we have chattering in the system, we imply that the equilibrium point is unstable. So the question now, what value of proving the, let's say, using the Lyapunov methods, the stability of the equilibrium point? So probably there is some value, but at least it needs to be reassessed, this value, because it's not an absolutely, let's say, correct result, I would even say, because when we say there is chattering, we say it's unstable. When we now start proving that this point is stable, there is a contradiction here, at least, and that you can clearly see. Also, chattering occurs in all parts of the system. It's not only that the output experiences these fluctuations, let's see. It occurs in all parts of the system, when they actuate a signal. And moreover, in mechanical applications, the most dangerous effect of chattering is not that these fluctuations of the output. It's the oscillations in the mechanical actuator, because this is a very undesirable mode for the actuator itself, because of the wear, and it may not simply last long in this mode. So that's the actuator problem, not the problem of the output in most cases. So again, chattering is a periodic motion and can be found from this harmonic balance equation. Chattering is unavoidable, and because chattering is instability of zero, as I said, Lyapunov analysis of stability and convergence so at least needs to be reassessed in terms of the applicability and the value of this analysis. What is then the alternative way to analyze this system? So, and I would say that we can, with the approach that that we will develop, we can analyze it as fast motions, as a composition, I would say, a combination of fast motions and slow motions. Fast motions is this fast chattering, and the slow motions is the average dynamics, average on the chattering, on the period of chattering dynamics. So that's the approach I offer to consider. So, two different systems. Just for reference, that we will, because I'm going to switch to slightly different notions here. If we have a hysteresis relay, and also a linear part here, for the hysteresis relay, we have this describing function which already has the imaginary part, and as a result, we in the harmonic balance, we are looking for the point of intersection of the Nyquist plot of the linear part and of this horizontal line, which is the negative reciprocal of the describing function, because negative reciprocal of the describing function is given here, has the imaginary part which does not depend on the amplitude. It is constant for all amplitude. It depends only on the hysteresis value B. B is the hysteresis value. So that's why this depends on the hysteresis. And here we have points, each point of this line corresponding to different amplitudes. So again, here we definitely we have a point of intersection even with the second order system, so it's obvious. Two-relay controller, which is a twisting algorithm. So let's say two-relay control is an extension of the twisting algorithm because we can excite oscillations not only in the second quadrant but also in the third quadrant. So this is given, the twisting algorithm is given by this equation with positive coefficients C1 and C2. Actually, C2 can also be negative. That's the thing. And the describing function is given by that one which I noticed on Leonid's picture drawn by his students, which I mentioned yesterday. Okay. And if we consider the negative reciprocal of the describing function now, this one, it is given by this formula. It is given by this formula. It has a real and imaginary part, but what is remarkable about that? That the ratio of the imaginary part and real part is a certain constant quantity. If we divide the it doesn't depend on A. It does not depend on A. It depends only on the parameters of this two-relay control. If we divide the imaginary part, because this is a certain coefficient, this is a certain coefficient. So it's only this equation and expression in brackets has a real and imaginary part. If we divide this imaginary part by the real part, we can see it's just C2 over C1. So that's why this angle is simply arctangent of C2 over C1. C2 over C1. So, and this is the negative reciprocal of the describing function of the two-relay controller. So now we need to look for a point of intersection again of the Nyquist plot and of this two-relay controller. We can say it's probably like fourth order system or fourth relative degree system. We have a point of intersection. If we had a third order system, we still had a point of intersection. For the second order system, we would not have a point of intersection. We would not have it. And here I come to the notion of the phase deficit. So again, considering this example of the two-relay controller, we can see that, let's say, this is the Nyquist plot of the second order system, and this is the negative reciprocal of the describing function for the two-relay controller, and this is the angle which is, let's say, what is the deficit here? I would say this is the angle that I should add as a lag to the phase of this Nyquist plot, so that the harmonic balance might happen in this system. And I call this angle phase deficit. So this is the phase that is, let's say, we short of phase, let's say, or phase lag that we short of to produce the phase balance and to produce the harmonic balance. So, and this is a very important quantity, because we can show that this quantity defines the rate of convergence in this system, in this let's say, transient process of convergence. And it defines the convergence time. It defines whether the convergence time will be finite or infinite convergence time. So if it is finite convergence time, then we will have a sliding mode. If it's infinite convergence time, we will have asymptotic convergence. So this angle is really important. And this is the rigorous definition of the phase angle. So we are looking at this part when A approaches 0 and of the describing function, and when omega of the Nyquist plot approaches infinity. So it's essentially that's the angle here. And I can explain it in very simple terms. This notion of the phase deficit. However, it is more, or I would say, way more rigorously established or proven by math from the point of view of the dynamic harmonic balance, which I'm not going to touch upon here. So the equations of the dynamic harmonic balance. Let me explain. For example, let's say we have a nonlinear controller, really, simply a relay. And here we have a linear part. And let's assume that the linear part provides it's not a very realistic scenario, but still, in some cases we can even artificially create this. Provides a constant phase lag, but which is still less than 180 degrees. Instead of 180 degrees, it can provide only, for example, 170 degrees of phase lag. What will happen in this process? Because oscillations must exist. Because if u is, let's say, +1 positive, y should grow, and then sigma, because it's negative y, should go lower. It crosses 0 and causes the switch of this relay to the negative value. And after that, the negative value results in a negative y results in positive sigma switches the relay in. That's the whole process. So oscillations would exist. But the harmonic balance cannot be established. So there are no oscillations of constant amplitude and frequency. So because there is no point of intersection between these two lines, we have a phase deficit here. So they do not intersect. There are no periodic solutions here. So what happens? There will be this phase deficit results in the switching interval shortening. So each next time T1 is large, T2 is smaller, T3 is even smaller, T4 is even smaller, and they are, this is for the control here, relay control. and y also responds to this signal as this process of also increased frequency and reduced amplitude. And specifically, so that's the switching interval shortening, the ratio of delta t, which is the let's say decrement of these time intervals, can be approximately evaluated as this. So pi plus argument of g of the plant, transfer function of the plant, at this frequency, this is a, I would call it instantaneous frequency, which is the 2 pi over this time, or actually it should be pi because it's half of the period. Pi over ti, and and basically this value in the numerator is the phase deficit in this case. This is the phase deficit. So this is 180 degrees, and this is the phase of the plant, which I said assumed, let's say, to be 170 or negative 170. That's why we have here 10 degrees, which we divide by 100 degrees, and this would be the ratio of this, let's say, ratio of the increment or decrement of the period to the period value itself in each next switching. So next, in this case, if it is constant, if this value is constant, assuming that this is constant, then they provide a geometric series. And the sum of the geometric series is given by that value, and as a result, we can say that the sum of all these switching intervals from 1 to infinity is given by this formula. So it is not infinity, it's a finite value, and this finite value depends on this phase deficit. So if the phase deficit is 0, then this right-hand side turns into infinity. So we have infinite convergence time in this case. If this phase deficit is a finite value, for example, 10 degrees, then we will have this, the sum of this will be equal to that. I put smaller than or equal to, assuming that, so it's assuming not constant value of the phase lag here, but depending on the frequency, but with high frequency the phase lag becomes high and reaches the maximum value at infinite frequency. So it's under that assumption. So that brings here this smaller than or equal to sign. Okay. Now we can say that if the phase deficit is a positive quantity, greater than 0, we have finite time convergence and sliding moment. If we don't, if it is 0, we have infinite time convergence or asymptotic convergence, let's say. If this value is negative, then we will have oscillations. That means we have a point of intersection. Okay, so that's what I already said. That's for this for the twisting algorithm, the phase deficit is given. For the super twisting is given. It is also found for some others. So another notion, propagation of averages. We said that we need to consider averages, fast oscillations, and averages separately. So how do we consider propagation of averages? So for this we introduce we consider the biased sinusoid and propagation of this biased sinusoid through relay in this case or through another nonlinearity, and find the average. So it's a sum of the areas, red areas minus the square of the blue area, which is given by this integral. And for many nonlinearities we can find. For example, for the hysteresis relay, it is given by this one. Now, describing function is a function of A and bias one of two variables. And if we now consider the, I would say, effective nonlinearity, I'm introducing this term here today for the first time. Effective nonlinearity for propagation of averages. Effective nonlinearity for propagation of averages. It is now not the original relay nonlinearity, or it is now not the original non-Lipschitz nonlinearity with the, let's say, infinite slope at 0. It is now a smooth nonlinearity, which is given by this formula, for example, for the relay. And it is a Lipschitz nonlinearity. So the averages propagate through the relay system or through the sliding mode control system is through a Lipschitz system. So for the dynamics of averages, we don't have finite time conversions because for them the system is Lipschitz. And in fact, we can replace, because this nonlinearity becomes sufficiently smooth, and we can approximate it by linear function at 0, so find the slope of this function at 0 and call it the equivalent gain. And analyze the propagation of averages as dynamics of a certain equivalent linear system. So here we have the bias function is an effective nonlinearity. So that's what the effective nonlinearity for the average dynamics. So it's not non-Lipschitz nonlinearity, it's a Lipschitz nonlinearity. And for the ideal relay, we can also find that the equivalent gain, which is the slope of this nonlinearity, is simply given by 2c over pi a, which is just half of the describing function, because describing function is 4c over pi a, not 2c. So implicitly we have kind of gain margin here of 2 when we consider the describing function and the average dynamics. Because why is gain margin of 2? Because in the describing function we have oscillations. We have a marginally stable system. And here we reduce this gain by 2 compared to the marginally stable condition, which gives us exactly the gain of 2. So that's an important point. And I call it an inherent gain stability margin because it's inherent with this system. We cannot change it. We add more elements, it still stays one half. We cannot modify it. Propagation of averages. So assumption, when we still made some assumptions. Of course, it is based on the harmonic shape of the oscillations, which are the input to the nonlinearity, not in other points of this system, but the input of the nonlinearity. We also assume that the bias function is quite similar to linear function when we replaced it with the equivalent gain. So we don't have to do that, but it would help. And external signals that cause bias, if the bias is caused by external signals, are quite slow compared to the oscillations. So that's the assumptions that we need here. And in this case, the dynamics of average motions are linear and can be obtained through the replacement of the discontinuous nonlinearity relay with the equivalent gain. So, which is shown here. So we simply replace this original system with this system, where we replace the nonlinearity with the equivalent gain of this nonlinearity. So this is dynamics of the average motions. This is what we use for the analysis of self-excited oscillations. And this is an example that I used in one of my papers. For example, we have this car and we control it through, we design a sliding mode controller, but we have a fast actuator, let's say second order actuator. As a result, we have chattering, but because of the gravity acting on this card, from the point of view of the ideal sliding mode, if we had an ideal sliding mode, we should not have the displacement of this card down this surface, because the sliding mode control would reject this disturbance, which is the gravity component. But when we have additional dynamics of the actuators, we have chattering, we have so now our energy dynamics are described not by Lipschitz discontinuous nonlinearities or non-Lipschitz nonlinearities, but continuous nonlinearities, equivalent gain. We have a displacement, and the simulations clearly show that. We have a shift of the from the zero position on this curve when we have in this position and try to maintain it at zero by sliding mode control. And the locus of a perturbed relay system, another method. So this is an exact method that I first presented in 1999. So this is an exact method, and this is applicable only to the relay control. So we have a relay control of the hysteresis relay. So we need, I assume the hysteresis relay. We can later set this hysteresis value be to 0 if we need it for an ideal relay. And this is a linear part. This is a linear part given by those equations. So we assume a certain asymmetric periodic process in the system, which can be caused by an external signal, for example. We apply a constant external signal to the input of the system, and we have a symmetric periodic process here. If we look back at the describing function method, so we, let's say, and we have this harmonic balance equation, we can say that we can notice that 1 over n is given, 1 over n is given, 1 over n is given by this one, this right hand side. And this is exactly 1 over kn, so it's the reciprocal of kn. So now we can rewrite the harmonic balance equation in this form. So here we have 1 over kn. And this part, pi b over 4c, that's the switching condition. That's when the output at 0 becomes equal to b. That's the condition, that's this condition. Output being equal to b. Output being equal to b. And here if we divide it by pi over 4c, so we have that this part is equal to that part. So let's define the function. Let's define the function as the right-hand side of this, but in such a way that these conditions are, let's say, satisfied exactly in this system. So we will start deriving these quantities and these quantities in the relay feedback system. So, and for this, yeah, that's what I'm saying. So this is, we will call this function the LPRS, locus of a perturbed relay system, as this expression. So these quantities, we require that they should be exact values in the system. So this is how we can rewrite the Kn as the ratio of the averages, limit of the ratio of the averages. Here it's because we started from the asymmetric process, y also f0 is the input signal here, constant input signal. This must become symmetric at this limit, and that's how we derive. So we start from the, let's say, equations as the reaction of the linear plan to the relay signal, find the Poincare map, find the fixed point of Poincare map by solving these equations. This is the fixed point of Poincare map. Then substitute them in this system closed loop conditions for the system. And as a result, we can say that we need this input to the system that would provide this asymmetry and this in this periodic process. And proceed to that, find from the definitions that we wrote the real part of the LPRS and the imaginary part of the LPRS, and eventually we find the whole expression for the LPRS. So, and we can see that here the LPRS is expressed only through the linear system or linear plant matrices, A, B, and C. It doesn't have anything else. And the frequency, because it's a function of the frequency. It's a complex function of the frequency. It has a real part and imaginary part. So these expressions. So this is a complex function of the frequency, and we can use it. That's another form which is produced through the Fourier series. So we can also produce similar result through the Fourier series, which sometimes can be also helpful. So now we can use it in exactly same way as the Nyquist plot. Nyquist plot we use for the harmonic oscillation. LPRS can be used for square type of signals that we have in the relay systems. So again, so this will be our LPRS in the complex plane. This will be, it's not a describing function anymore, but a similar condition, because it's a, I would say this line defines a switching condition now. Also pi b over 4c, because it was designed as an imitation of this describing function and harmonic balance principle. So LPRS is a replacement of the Nyquist plot, and all the rest remains the same. So instead of Nyquist plot, we use the LPRS, and also find a point of intersection with this line here, which gives us the frequency. It doesn't give us immediately the amplitude, because we don't have we don't have dependence on the amplitude here, but we can find it later. And this point gives us the frequency, and the same point gives us the equivalent gain. So this distance is a reciprocal of the equivalent gain. So we can find the periodic motions, and we can find the dynamics of the average motion in this system. So again, if this is our original system, for the dynamics of the average dynamics is given by that one, where Kn now is found from the LPRS and represents the exact value. So we don't have, we remove quite a number of assumptions that we had in the describing function system. There is a whole algebra of the, I will briefly just go through this slide. For the first order, that's the LPRS. For the second order, that's the family of LPRS for different values of zeta here. Second order integrating, double integrator goes here. Third order dynamics, like that. So we can also notice that we have some, let's say, features of the LPRS. If it is given by the, let's say, ratio of two polynomials, and the relative degree is greater than 1 or greater, then the, let's say, zero frequency of the LPRS can be found through that one, unless it is not integrated. For integrating, we have other, let's say, the formulas. And the infinite frequency will be 0. Also, we can find that the high frequency asymptotes of the LPRS are exactly the same as for the Nyquist plot, which is also a very important feature. We can easily, let's say, apply the properties that we found for the Nyquist plot to the LPRS and use the same analysis. Okay, so same conclusions regarding the parasitic dynamics. The methodology of analysis again the same. So here again we have in dashed line first order we don't have oscillations. In solid line, dotted line, we have periodic solutions, periodic motion. I will skip a few slides. Chattering, it's pretty much the same conclusions that I already mentioned. Now, 4 conditions of the realizability of the periodic motion. That's also pretty interesting, I find. So first, this equality must be satisfied. So where the this is the equation from which we find the frequency. In addition to that, orbital stability or the found periodic motion must be satisfied. This is the orbital stability condition. So this matrix must have eigenvalues smaller than 1 in magnitude. And the candidate periodic solution found to must have the proper direction of switching of the relay. It was clearly established by Zipkin. And candidate periodic solution assures no additional zero crossing of the plant output in the open loop test. Zipkin. And chaotic chattering. This is a very recent result which was produced by my former PhD student, myself, and Dr. Yahya Zveri. So if conditions 3 or 4 that I mentioned before are violated, then we can come to chaotic chattering. There may be some intermediate modes there, but so at least this is like for chaotic chattering, this is necessary conditions, is the violation of these two conditions. Analysis of closed loop performance, basically the same through the Kn, equivalent gain, I mentioned it already. And here we can conclude what's the difference between the ideal sliding mode and non-ideal sliding mode. So in ideal sliding mode, chattering exists only in control signal, output has no chattering, let's say, because it's filtered by the plant itself. Here, from the LPRS, chattering exists in all state and the output signal. In ideal sliding mode, disturbances matched disturbances do not have any effect on system states and the output signal. Ideal disturbance rejection. Here we will find that disturbances are not fully rejected. Rejected properties are defined by the equivalent gain. In ideal sliding mode, ideal tracking of input signal can be ensured. In LPRS analysis, ideal tracking of input signals cannot be ensured. Tracking performance depends on the equivalent gain. Another interesting result which fully supports the value, the numeric value of the Kn that was found. So this is the paper by these authors. So we have the plant as these dynamics. And this system has 3 periodic solutions. 1 symmetric, yellow, and 2 asymmetric periodic solutions. And we have a bifurcation parameter D. We found by the LPRS method what value of D must be so that which in D defines Kn. D defines Kn. So it's what value Kn should have and D should have, respectively, to provide the bifurcation between symmetric limit cycle and asymmetric limit cycles. The stability of symmetric limit cycle is violated at exactly this value, up to like 10 digits. We investigated up to 10 digits, and simulations show exactly the same value. We used like a high performance machine to show that. So it's exactly these values with this number of digits, because this blue line, this is -1 and 0, the critical point of the Nyquist plot of the linear path, which includes Kn, and Kn is found through finding of the periodic process and the LPRS. Here we have unstable linear part and stable linear part, and as a result, whatever is right on this point, we have a symmetric, stable symmetric limit cycle. Whatever is left, this limit cycle is not possible. I will skip this example and some. I will go to some, maybe a few more minutes. Modified relay feedback test, and which is, I mentioned yesterday, this in our answers. This is basically suboptimal algorithm with a different sign of the parameter, this beta, to excite oscillations specifically, rather than to bring it to a sliding mode, to excite oscillations. So, and if our transfer function of the plant, so this is a test. This is the algorithm that we use for testing to excite oscillations, measure the frequency and amplitude of the oscillations, and use them for tuning. So if this is the controller, PID controller that we are going to tune, and this is the reciprocal or the describing function of the MRFT. So, and we can show that this is the reciprocal or the describing function of MRFT, which is a straight line, like in a two relay controller. And if we have a point of intersection, we have oscillations. Now, if we measure these oscillations, we will use these tuning formulas where amplitude of the oscillations that we measure and frequency of the oscillations that we measure. But if we first perform MRFT with this value beta, which satisfies these coefficients, and later our coefficients, and our coefficients C1, C2, and C3 in these tuning rules that we call tuning rules satisfy this equation, then we have a gain margin tuning with this value of gain margin. And we select beta for the test satisfying this equation, and our C1, C2, C3 satisfy this equation, then we have phase margin tuning with this value of phase margin. For example, for gain margin of 2 and PID control, we have C1 of 0.46, C2 0.5, and C3 0.12, and we perform the test with this value beta, we can guarantee that we have gain margin of 2. And this is what is a remarkable thing here. For any system without identification of the plant, without knowing what its dynamics would be, we can guarantee that if the control is designed using these tuning rules, and if the test is done with this value beta, we guarantee the gain margin of 2. The same thing is for the phase margin. If we, for example, if we run the test with this value beta and our coefficients C1, C2, and C3 are those, we guarantee the phase margin of 45 degrees without identification and knowing what the plant is. So we can do that. However, it actually opened a new way, because in these equations we have some freedom. We have here we have equations for beta. Basically, we have 4 parameters: beta, C1, C2, and C3, and we have only 2 equations. 2 other parameters are free. We can vary them. And we can optimize them. And this what led to the new paradigm: optimal process-specific non-parametric tuning. So this is this must be a separate topic, a topic of a separate talk, I would say, because it's necessary to explain this concept. But we can first formulate the problem for a class of systems given by a model with ranges of parameters. Find a set comprising these parameters C1, C2, C3, and the test parameter beta, or similar for the two relay controller, also ratio of two amplitude, such that provide the best performance of samples belonging to this test. The term best performance can be mathematically formulated in a few different ways. And we formulated it as minimum of gross deterioration of interval performance with respect to optimal performance. And this is for a set of models, or class of systems. For example, class of let's say certain loop tuner was made for flow loops, or level loops, pressure loops. These are the classes of systems for which the tuning rules were produced. Or for the UEV that you saw yesterday, at least some of you saw yesterday. Or auto-tuning of Buck and Boost converter, which we also had a project with. Or auto-tuning of satellite controllers, which you also might see yesterday. Or auto-tuning of underwater vehicle, which is the current project right now. And I would probably just conclude with the, I was going to show you maybe one or two videos. So that was, oops, I'm sorry, I don't know how to, this is not okay. One second. That's a different video, but anyway, that's what you didn't see yesterday in the, like a complete format. So it's untuned photos, and here 5 controls that are being tuned. So it's here, whatever is in green, it's completed. The tuning is complete. So, and here we have here, okay, now all of them are, no, this one, so all 5 are complete, because here we have pitch, roll, Z, Y, and X. So these are the controllers that are being tuned to. And now it passes through this window. After this tuning from completely untuned to fully tuned and even optimally tuned stuff. And that is even at the minimal theoretical speed, because it cannot, the speed cannot be smaller than a certain value. And I don't know if you saw it yesterday. So this is the two-relay test of the satellite. I'm not sure if you showed it yesterday. Okay, yes, so you saw it. So that's what it is. And just let me conclude. Maybe I can conclude without help of the slides. Basically, sorry.
Please show the slide again.
Please show that.
Yes. Thank you.
Just one second. Slide show from slide. And I will go down. No, just. I better. Yeah, okay, conclusions. Presented frequency domain methods, DF-based, harmonic balance phase deficit, and LPRS-based, show a spectrum of analysis and design problems and their solutions that are different from the traditional state-based methods. The main advantage of the presented methods is the absence of constraints on the system order. So it's any order of the system. And the limitations are related to approximate character of the describing function based methods and the relay feedback structure of the LPRS method. So it's only relay feedback structure. For sliding mode control system analysis and design, we can draw the following. Sliding mode control system is a special type of relay feedback system. Its principal dynamics has relative degree 1, and the relay has no hysteresis. By the principal dynamics, I understand the one which produces the ideal sliding mode without considering actuators and sensors. The presence of actuator and sensor results in additional dynamics and the increase of the relative degree. This in turn leads to chattering. The presence of chattering transforms the original non-Lipschitz nonlinearities into smooth, effective nonlinearities or bias functions, and this results in non-ideal closed-loop performance of average dynamics. So for average dynamics, it's not non-ideal. The use of the presented methods of analysis and sliding mode control system can bring new level of accuracy and realism. It is important to understand that real sliding mode control systems are not absolutely robust with respect to disturbances and uncertainties. And the presented methods clearly explain this conclusion and allow one to obtain realistic estimates of robustness. Finite time convergence to zero in the context of sliding mode cannot happen in real life because of the transformation of original non-Lipschitz nonlinearities into smooth ones. The level of proof of stability based on the models that doesn't contain additional dynamics gives the conclusion that does not agree with practice because of chattering, which is a manifestation of instability. And why the use of the considered frequency domain method would make a lot of good sense to the control engineering practice and be of educational value. Some recommended, let's say, references about the LPRS and the phase deficit. Thank you very much. I'm sorry, I started 7 minutes later and it took me 10 minutes more than that's it. So, sorry about that.
Okay, it was fantastic. Thank you. So, I don't know if we have some time for a question.
Maybe we go for the
At least I would like to
Do you
applaud first.
Thank you very much.
Igor, could you please answer a couple of questions if they are?
Okay. So we need to run, yeah, but
Yes,
I will
let's run.
happily answer your questions.
Very short.